Hello, my name is David Strain. I'm president of APS. It's a small systems development company in Canada. The device you just saw operating is a hydraulic displacement motor. It's a self-contained system which runs itself. In fact, generates more power than it requires to run itself, and that's why you can see the Canadian flag flapping back and forth. The video which you're going to see will enable you to understand the circuitry completely. The most important 2 points in the system are to understand how we develop the greater volume, and secondly, how we develop the greater force at the tip of this actuator. In this demonstration, we'd like to create an understanding of how we establish a volume increase with respect to the new diamond-shaped piston.
To first understand the concept behind the diamond-shaped actuator, we must first look at a standard actuator. These devices have been in use since the Industrial Revolution and through machining have become highly efficient. Looking at a simple actuator, we can see how applying a force on one side of the piston will force the shaft to move. The force of the movement is the result of two major factors: the pressure on the piston and the surface area of the face of the piston. The larger the face, the more the force. In this scenario, two actuators of equal size are pressurized. As the faces are of equal size, the forces are equal, thus no movement occurs. However, if one of the faces is increased, it will exert a stronger force and overpower the smaller. There are other configurations of actuators. The diamond-shaped actuator. This is not a new concept, in fact dates back to 1874. In this configuration, the single flat working face of the conventional actuator is replaced with a four-sided hinged box. To be accurate, a rhombus. As pressurized fluid enters, it presses against the walls and the rhombus changes shape and the shaft is driven forward. The advantage of the diamond-shaped actuator is that it produces more force through equal travel than a conventional actuator with identical fluid input.
Now, a very critical point which we have to address next is that if we don't have enough force pushing this way off of the diamond-shaped piston to overpower the counter force in the conventional piston, then we'll get no movement. So the next demonstration will show you that we do get a substantial amount of surplus force going that way over the counter force pushing back from the conventional piston. This demonstration was set up to allow you to see the force development at the tip of the diamond-shaped actuator. You saw how the diamond-shaped actuator expands. What we had to do is assess the total force at the tip of the actuator pushing upward, and in order to do that we had to know very accurately the pressure within the diamond-shaped actuator, and we also had to know very accurately the amount of weight that it was lifting. Now, to address the pressure portion of it, we have a 0 to 10 pound gauge here, which is a fairly tight range gauge. We have a 0 to 80 inch water gauge, Magny-Hilt gauge onto the same line, which again is a very accurate gauge. And to complement both of those, we've got a water column we set up with purified water through reverse osmosis, so we could read the inches of water gauge pressure to within about 1/10 of an inch. So we have very accurate means by which we can know the pressure within the diamond-shaped actuator. Now, the next issue was the weight portion of it. We bought this 50-pound weight from a scale company. I watched them cross-check it with a certified weight. It's within 5/1000ths of a pound of being accurate to 50 pounds. We took bought a digital fish scale and took the scale to the same scale company, and we used that to lift on this wire with the weight off of it to lift the total linkage, so that we could add the linkage weight to the scale, or to the steel block weight, and there's a total load that the diamond-shaped actuator has to lift of a little more than 60 pounds. So that's why our calculations are based on 60 pounds. Now, what we currently have is a digital caliper on here, which allows you to see the physical movement here. We've got the weight sitting up and it's supporting the diamond-shaped actuator supporting the weight. Okay, what we're seeing at this point is the diamond-shaped piston has pressure in it at 2 1/4 pounds pressure, and we're sitting at 15.55 millimeters of drive on the digital caliper. I'll turn the pressure in the diamond-shaped piston to a lower value, 1.8 pounds instead of 2 1/4, and it won't have enough pressure in it to generate enough force to hold the weight. and the weight will start to drop. You'll see the digital caliper's value start to decrease. You see the digital caliper dropping. So I'll let it drop down for a bit, and then I'll throw the pressure back to 2 1/4 pounds pressure again in the diamond shaped piston by this switch, which is it'll stop the fall of the weight and actually start to lift it back up again. So we're right now at 7. So now you see it's starting to lift. We're down to 7 point something, and you're up at 8 point something. It stopped the fall of the weight, reversed the fall, and started to lift the 60 pounds of weight. Now, had this been a conventional piston, it would require not 2 1/4 pounds just to hold its equilibrium point, just to break even. It would need 2 1/2 pounds. So what this demonstrates is that at this particular number of degrees of rotation for the diamond shaped piston, it has 11% more power, or in excess of 11% more power than what a conventional piston would have if the conventional piston had a face area equal to the face area of one side of this diamond shaped piston. In the previous demonstrations, we established the means by which we gain the volume increase in displacement by using a diamond shaped piston pushing fluid out of a conventional piston. And in the second demonstration, we established that the force at the tip of the diamond shaped piston is in fact greater than the counter force of a conventional piston if it has the same face area as one wall of a diamond shaped piston. So we have to put these thoughts together in order to start to develop a thought process into the running machine.
In this scenario, the working face of the conventional actuator is 10 square inches. The 4 sides of the rhombus are 10 square inches each, giving the diamond shape a total working force of 40 square inches. As the pressure increases, the diamond-shaped actuator overpowers the conventional actuator by 20%. There is, of course, some loss due to friction in both actuators, but overall, there's a net gain in force. Just as in a standard gasoline engine, one explosion in one cylinder would just allow one cycle of force generation. A complex set of controls are used to return the device to its start position, and the cycle is repeated. The diamond-shaped actuator produces its own source of fluid by pushing it from the conventional actuator. Again, some energy is lost to the reset, but the overall outcome is a gain in energy. Free energy.
Okay, what we've demonstrated in this video is that when a diamond-shaped piston displaces fluid out of a conventional piston, the diamond-shaped piston's face area along one wall is equal to the face area of the conventional piston. The amount of fluid displaced out of a conventional piston is greater than the quantity of fluid required to create the displacement in the diamond-shaped piston. We've also demonstrated that with the same pressure of fluid in each of the pistons, the conventional piston and the diamond-shaped piston, the diamond-shaped piston will generate greater force and will force the fluid out of the conventional piston. Now you see this model operating, and it's moving the Canadian flag. The total force moving forward on the diamond-shaped piston on this particular little model at 95 pounds pressure inside is 125 pounds, but we have 125 pounds more force pushing this way than the counter force pushing back, and that's why the diamond-shaped piston forces the fluid out of the conventional piston. It waves the flag, and it obviously do a lot more work than just do that. Now, just to follow through on the thought of the power, in this model, we were operating with pressures at 2 1/4 pounds per square inch. That's not the normal operating pressure for hydraulic systems. If we were to increase the force within this model to 10,000 pounds per square inch pressure, this particular model at this size would generate a surplus lift of 20,000 pounds over 2.5 inches. And therefore, if you take it and build models that are the size of this room, you're going to end up generating millions of pounds of lift over a few feet, in which case you'll be able to run power plants.
If you wish to know more about this, we have a free training manual on our website and also articles that explain a lot of the science that we've worked on, both in the HVAC area where we've reduced buildings' energy consumption by as much as 50%, and we're willing to share that logic with every part of the industry, and it'll be significant with respect to reducing global warming. And then also there's another part in that website. One of the articles is Fighting Climate Worry, and within that article we have links to a student logic course which will allow you to understand the logic of this full patented device which is done internationally. The kids are relying on us to look after them, and the government really isn't doing its job in my mind. And if you don't speak up for the sake of your children, the statement by a gentleman named Brian Kelly, who used to be the sustainability manager of the Durham region in Canada, he resigned out of frustration for the lack of action from that region. And his statement was, do you want to explain to your children and grandchildren why you did not have the courage to protect their future? That's a very serious issue, a very serious statement that he made, and hopefully everybody will consider that and pull together to try to help to protect the children's future.